All right, so welcome back to another chapter quiz walkthrough. Here we're going to be working on chapter 10 for the chapter 10 quiz. So I'm going to try something a little bit different. So what's the maximum number of valence electrons for most elements? This is a multiple choice question. So the maximum number of valence electrons for most elements is going to be eight valence electrons. And that has to do with the number of rows. Well, it's related to the number of rows on the periodic table. But if you ever forget, you can always look back to that and remember that we count valence electrons as we move across in the S block and the P block. So for our next question, how many electrons is a double bond worth in a Lewis dot structure? So here you got to know that each bond equals 2 electrons. So if we have a double bond, it means exactly what it sounds like. So if we had something like carbon with a double bond to oxygen, there's 2 bonds there, so then that's 4 electrons. All right. How many valence electrons does strontium have? So here you can go and you can look at the periodic table. We have strontium. It's in group 2A. Or group 2, that's the second column on the periodic table. And the shortcut that you can use is that the group number is equal to the number of valence electrons. You do have to remember though that when we get to sort of the right side of the periodic table, right, so we got the periodic table kind of looks like this. Over here, we're going to have these columns. I think that's right. 1, 2, 3, 4, 5, 6, 7, one more. 8. So this is going to be, there's 2 columns over here, 1, 2, 3A, 4A, 5A, 6A, 7A, and then 8A. Kind of ran out of space a little bit there, but that's the idea. So that these numbers are also the number of valence electrons. So strontium is over here in column 2, or group 2, so we have 2 valence electrons. Okay, so now we're moving on to this next question. We have match the following elements with the correct number of valence electrons. So we got a bunch of these. We have lithium plus, we have gallium plus, phosphorus, sulfur 2 minus, carbon, nitrogen, notably with no charges, radon, fluorine, fluoride with a 1 minus charge, and then lithium here without a charge. So the key point here is that, so one of these is actually incorrect. So lithium, now that I'm looking at my key, lithium only has 2 valence electrons. Right, so these are all, and that's because lithium is over in the S block here. So this is hydrogen's up here. Lithium is here. So then on our periodic table, which will look something like this, if we remove 1 electron from lithium, now its valence electrons are the same as helium. So we have 2 valence electrons. So that was a typo on my part. I'll go back and fix that in terms of points. For basically everything else though, gallium plus, sorry, it's not plus, it's 3 plus. Gallium, I should have pulled up a periodic table for this, but I didn't. Gallium is actually over here. Gallium's a little bit trickier because these D block electrons are not part of the valence electrons. They're always 1 principal quantum shell below the highest. So then when we take gallium, we have gallium here, we have gallium right here, and we do minus 1, minus 2, minus 3. So then we have the same number of valence electrons as argon, I believe it is, but that's 8 valence electrons. Neutral phosphorus is going to be over here, not above gallium, but somewhere over here. So that phosphorus is then going to have let's see, what group is it in? It's in 5. So phosphorus is in group 5A. So because it's a neutral atom here, it has 5 electrons. So I should have mentioned this before. Anytime we have a positive charge, we're removing valence electrons. Anytime we have a negative charge, like our next question here with sulfur, we're adding electrons. So sulfur, neutral sulfur, sulfur with a 0 charge, has 6 electrons. But because we have this 2 minus, that means we're adding 2 more electrons. So sulfur 2 minus will be 8 valence electrons. Carbon is in 4A. So carbon has 4 valence electrons. Nitrogen is in 5A, so it has 5 valence electrons. Again, both of these have neutral charges. Radon, moving to a different part of the periodic table that we don't normally go to, but radon is a noble gas, so it has, and it's in column 8A, 8 valence electrons. So a lot of these are going to have 8 valence electrons. Fluorine, again, right? So we've got fluorine, F1 minus. So let's back up a step here. If we have F0 and we're looking for F1 minus, fluorine is in column 7A, so that's 7 valence electrons. Fluorine, because it has a minus, fluoride I should say, because it has a -1 charge, is going to be 1 more electron. So we're going to give 8, so again 8 valence electrons. And now we have neutral lithium. So neutral lithium is in group 1A, so it has 1 valence electron. So the point here is that really you can just look at the periodic table, and all you need to know is that the group number for the neutral element, let me write this out. So the group number for neutral element, and specifically here, this is a neutral element, so neutral meaning 0 charge, is equal to the number of valence electrons. And then a positive charge indicates 1 less, or I should say 1 less electron than neutral. And then 2 positive charges would be 2 less. And a negative charge indicates 1 more electron than neutral. Okay, so we're going to look at question 5. And for this question, we've got multiple steps that you have to carry out. For number 1, we have to write the Lewis structure for sodium chloride, Na. Cl. There's something wrong with my Apple Pencil. And so the first step is going to write sodium, we're going to write chlorine, and then we're going to find the number of valence electrons on the periodic table, which you should be able to do by now. Sodium has 1 valence electron, and then chlorine has 7 valence electrons. And the key for this problem is that this is an ionic compound. So when we're writing this out, we're going to have sodium with its single valence electron, and we're going to have chlorine. It's going to have 1, 2, 3, 4, 5, 6, 7 valence electrons. Now, we know that our compounds always want to form, bonds so that they have 8 valence electrons. So when sodium and chlorine interact, because this is an ionic bond, we're going to get a complete transfer of this single electron from sodium to chlorine. So when we write that Lewis dot structure, it's going to look something like this. So we've replaced these two, taken these 2 electrons and turned them into a bond, which we indicate with a line. And then it's 1, 2, 3, 4, 5, 6. So in some ways, the ionic compounds are actually easier to balance and easier to write Lewis structures for than molecular compounds with covalent bonds, or even polar covalent bonds. Because now what's happened is, by giving up this electron, sodium actually has its full valence shell from the layer below. So it'll have the same electron configuration as neon, which is going to be 1s2, 2s2, 2p6. So these 2s2, 2p6 are now sodium's valence electrons. And it's happier with that configuration. For number 2, I'm going to write the Lewis structure for nitrate. So this is a polyatomic ion. We'll start here by writing out our central atom of sodium, and then drawing bonds between our outer atoms, which are going to be oxygen. Now we're going to write out nitrogen, oxygen, and then our charge, because our charge is going to change the number of electrons that we have. And here, because we have a -1 charge, we're going to add 1 extra electron. So nitrogen is going to have 5 electrons, oxygen has 6 electrons. We're going to multiply that 6 by 3 because we have 3 oxygen atoms, as seen here in our skeletal structure. And also the 3 here in our formula. So when we do this math, we're going to get 5 plus 18 plus 1. That'll give us our total number of valence electrons. So it's going to be 19 plus 5 is going to be 24 electrons. Okay, and then we've used, based on our Lewis structure, or our skeletal structure here, we used up 2, 4, 6 electrons as our bonds in our skeletal structure. So because we have 3 bonds, that's 6 electrons. So we're going to have remaining electrons to distribute, and that's going to be our valence electrons minus our bonding electrons. So that'll give us 18 electrons left over. And when you distribute these, you want to do them in pairs, and then you want to distribute them evenly to the outer electron, or to the outer atoms first. So go 2, 4, 6, 8, 10, 12, 14, 16, 18. Now, when we take this structure here that we have, our next step is to count the number of electrons that each atom has. So these bonds count as shared electrons. So for our nitrogen, we'll have 2, 4, 6, but we want to get to 8. So we're going to have to do something to get to 8, but let's go check the rest of our atoms first. So this one, oxygen, has 2, 4, 6, 8. Because those bonded electrons are shared, we count them for the atoms at either end of the bond. So for this top oxygen, it's going to be 2, 4, 6, 8, 2, 4, 6, 8. So in order to give nitrogen its full 8 electrons, what we'll have to do is take a pair of electrons from one of these oxygens and form a new bond, making the single bond a double bond. So we're going to do just that. Let me show this. We'll be taking these electrons and adding them here to make a new bond. So nitrogen, oxygen, double bond here now. And because the electrons in the bonds are shared, this oxygen didn't lose those 2 electrons. It just now has 2, 4, 6, 8. And we can now count this extra bond in nitrogen's electrons. So 2, 4, 6, 8. But we didn't change any of the electrons on these guys, so they remain the same. Okay. So this would be a correct Lewis dot structure, but we need to add brackets and this minus sign outside the brackets to match the charge on our ion up here. This one can also form resonance structures. So the resonance structures would be similar, but now we're going to move that double bond and form it between a different oxygen. And for this one, actually, let me give myself a little more space here. So this would still be -1 charge. And then we can do this again with the remaining oxygen that we haven't done it with already. Oops. So there would be all three of our resonance structures. Okay, moving on here. For 3, we have AlCl3. So take a minute here, take a look at this, and what kind of bonds are we forming here? And how do you know that? So I would pause, try and think through that. You should notice that aluminum is a metal and chlorine is a nonmetal, so that means we're forming an ionic bond. You might also use at this point knowledge that you have of electronegativity to actually calculate the electronegativity difference, and that can tell you about the character of the bond. But we can start it here by simply writing out aluminum, and then I'm going to draw 3 lines because we have 3 chlorines. So those lines are the bonds between those chlorines, and that's the minimum number of bonds that we can have. Because if we didn't have these bonds, they wouldn't be attached to each other. It wouldn't be a molecule. Or in this case, a formula unit for an ionic compound. Okay, so we've got aluminum, right? We need to know the number of valence electrons that we have. Aluminum has 3 valence electrons. And chlorine has 7 valence electrons, but we have 3 of those, so we multiply by 3. So this will give us a total of 21 electrons and 3 electrons. So our absolute total of valence electrons then is going to be 24. And then we've used 3 of those electrons, or sorry, we've used 3 pairs, right? We have 2, 4, 6 electrons in our skeletal structure that we used as bonding electrons. And then the difference between these, so 24 minus 6, is again going to be 18, like we saw in our last one actually, remaining electrons. And those are the electrons that we'll take, and we'll go 2, 4, 6, 8, 10, 12, 14, 16, 18. So the tricky thing about this question is that aluminum is special. And if you look on the periodic table, we've got boron, we've got aluminum, we've got gallium, because I believe gallium does this too. These can form compounds that have, where boron, aluminum, and gallium only have 6 electrons. So they'll only form 3 bonds, and they'll be happy with that. So for this problem, this would be our finished Lewis dot structure. Okay, moving on to number 4. Number 4 inside of question 5. Here we want to write Lewis structures just for these individual elements. So we're going to have hydrogen, we're going to have bromide, because the negative charge there makes it an ion. We change the ending for ions, and boron. So hydrogen, just look at the periodic table, has 1. Bromide is going to have 7 electrons, and then plus 1 more electron for its charge. So it'll be 1, 2, 3, 4, 5, 6, 7, 8, right? Because this equals 8 electrons. And then boron, we can use its position on the periodic table to figure out how many electrons it has. So it has 3 valence electrons. And that would be the appropriate Lewis structure. All right, let's move on here. We're now on question 6. And for question 6, I have to do a Lewis dot structure for gallium iodide. So it's going to be gallium, and we're going to have iodide. And the key here is that I wanted you to use the Lewis structure to predict what the structure of gallium iodide should be, rather than using the other stuff that we've learned already for this class. And what you should find is that the Lewis structure that you draw will match that which you would predict simply based on the charges on gallium and iodine that they most commonly form. So, like all of our other things, or actually, I should say, this is a little bit different in the procedure that we got to take. So let's write gallium down. And let's actually just write the number of valence electrons that gallium has, which is going to be 3, because it's in column 3A on the periodic table. And iodine is going to have 7 valence electrons because of where it is on the periodic table. So if we write gallium, and remember, because of Hund's rule, we put these electrons on our atom one at a time. We don't pair them up first. We'll pair them up afterwards. And then we can write iodine in a similar way. So if we write these out singly first and then doubly, what you should notice is that this single electron and this single electron, if they formed a bond, then iodine could have all of its valence electrons. The other thing to note is that gallium is one of our special elements that I mentioned up here before. Boron, aluminum, gallium. It only needs 6 electrons. So we can say, okay, well, how many iodines are going to bond with gallium? Well, gallium's got 3 electrons, and it wants to give away those 3 electrons because it's a metal. So if we then draw another iodine, all right, again, similarly with 7 electrons, and then another one, well, gallium can give away 3 electrons. And it can do so to each of these iodines. Because then that would give gallium the same electron configuration as argon, which would mean it has 8 valence electrons. So our Lewis structure then would be gallium, iodine, iodine, iodine. And then these would all have the rest of their electrons as well. So gallium has 6, and that's fine. And this is an ionic compound. So our formula then, based on this Lewis structure analysis, is going to be gallium I3. And then the most common charge formed by gallium, 3+, which would be our gallium with its 3 electrons. If it gives away these 3 valence electrons, then it's going to have a 3+ charge. And that's why this is the most common ion that it forms. For iodine, most commonly forms a 1- charge, because if we have iodine with 7 electrons, and it gains 1 more valence electron, it's going to have a minus charge. So when we combine these together, our 1- charge needs to cancel out our 3+ charge based on the way we were doing things before, or that we previously learned in this class. So you're going to need gallium, and then you're going to need 3 iodines to balance that charge. So now our overall charge on gallium is going to be a +3. Our overall charge on iodine is going to be a -3, which will equal 0. All right, one last question. Question 7. Pull it up here real quick. In a covalent bond, so this is a true-false. In a covalent bond, electrons are shared between elements. One of the ways that you can think about this is just by looking at the word covalent. So co usually means together. You know, codependent, company, collaboration. These are all words where it's groups of people working together. And this is covalent, which is just another form of the word valence. Oops, not valences. Another form of the word valence. So this is together valence. So in a covalent bond, they are sharing, they're working together in their valence electrons. So in a covalent bond, valence electrons are shared. This is true. Okay, that's it for this quiz. Hopefully that's helpful. Make sure you study up on all of this stuff. I think in particular electron diagrams and electron orbital diagrams. All right, make sure and reach out to me if you have any questions.